So this is actually the panel for the quantum black hole. So we have actually 4 panelists. Actually, I just name from here. Actually, Dr. Eduardo Wilson, Aileen, and Christina, and also Carl and Abe. So and also we have Alexander. He's actually remotely. So our actually we have totally 55 minutes. So this actually the schedule, 10 minutes for each of the panelists, takes a couple of minutes to give an outline for future research on quantum black hole. So please try to, each of you within 2 minutes. Okay, thank you. Yeah, then we are actually about 30 minutes to the questions from the general audience. I will first start with the questions you already signed to the list, which is 11. So if we finish all of them, still have time, I will actually pass this to current audience to ask questions. Then actually the last 15 minutes will be the panelists ask questions each other. So let's start from the panelists. I think the first transparent is the Karas. So please.
This is me, I think. 2 minutes? Okay, so in the conference there have been various people talking about the picture of the black holes, that of the future evolution of black hole, which I find more convincing at present. I should say that I've changed my mind about this a few times, so my evolve. I have this just single slide. It's what I expect is summarized in this picture here. So the full life of a black hole, I think, is a strongly irreversible phenomenon dominated by dissipation, by reversibility. To start with a compact star and ends up with a spread out radiation. The key part, which is the most interesting, is what happened at the end of the evaporation, the deep quantum gravity region, and that part can be described, at least in first approximation, with a time reversible phenomenon. I think it should be analyzed in pieces, what we call the A, B, and C region, the matter part, the sort of pure gravity part inside the hole, and what happened at the horizon. Because they're different. I got convinced, contrary to what I wanted before, that what happened at the horizon is a non-analytic H bar. So it's a genuine sort of tunneling phenomenon. The picture has been detailed by Farshid, by Francesca, by Kong, by Hongu, by various people during this this talk. And for those of you who were at the school, I gave lectures on that. And very briefly, the energy comes up mostly with a Hawking radiation. That's what we expect. But the information goes inside and come up later in the sort of picture that Abai has in mind since his work with Borchewald. And this picture is very compatible with the lower dimensional model that Abai carefully was describing in his lectures. I think that the other phenomena which have been explored, like Alejandro's dissipation into microscopic black holes, or the shockwave that Ed and Vicar, the collaborator, are super interesting and need to be studied more, but I am not convinced that they disrupt this basic overall picture. Most interesting aspect of that for me is that if this happens, this gives, that was my short talk yesterday or the day before yesterday. Most interesting all these stories that the theory indicates existence of a particle of the Planck scale, which can be detectable, can be a component of dark matter. So it's not a strong prediction, but a strong indication which follows from the area gap, which seems to me the most interesting aspect of all this story. And my suggestion is that that should be better understood.
Thank you. Christina? Yeah, I think I'm going to, yeah, okay.
Oh, thank you. Yeah, I would like to go back to the point where basically the discussion on symmetry-reduced models started in the context of cosmology. This was 1999. yeah, when Martin Boyewald and Kastrup started to do that, and then a few years later, there was this paper on the mathematical foundation of symmetry-reduced models in cosmology by Jurek, Abai, and Martin. And from that on, we have, many people have explored those models, have obtained very interesting insights. And also there's a kind of effective theory has been developed, their relation to the quantum dynamics, and even not restricted to the canonical setup. Also, we saw on this conference many talks on GFT cosmology and spinform cosmology. Now going to spherical symmetry with a perspective from the full loop quantum gravity theory, it's a very interesting model, which is a bit broader because it's a 1 + 1 dimensional field theory, and we have a non-trivial diffeomorphism constraint, so we can address different questions than in cosmology. And also we have very nice applications to quantum black holes. Next slide, please. So people have explored, no, the one before. So people have explored Dirac quantization also for quantum black holes. Jorge Pullin, Rodolfo Gambini, Miguel Campilla, and Javier Olmedo. None of them is here, so I thought I should highlight this a bit. And also we have a lot of effective models and analyzed properties of these kind of quantum black holes that we are interested in. Many people contributed. And the point of view we addressed in our recent work was a bit to understand basic properties of these models, which many models might have in common. So define, in a sense, class of models and a few assumptions, and then understand how restriction on the quantization, respectively polymerization, might identify models or might determine their physical properties. Now, this was still only at the effective level, so a future step, I think, from my perspective, that would be interesting is to get the insight we obtain at the effective level, go back to the quantum dynamics and see whether we can carry over some of the insight back to where we started from, at least in the quantum cosmology context, also then here in the spherically symmetric context. Thank you.
Thank you. Ed?
So I'll just say a few things from the perspective of the work that I've been doing with my collaborators and that Ricard presented on Tuesday morning. So there's been a lot of work looking at models in vacuum and recent progress looking at these dynamical collapse models, still looking at these effective models. And some of the results that we've found in LTB collapse are that we have, during collapse, the formation of two horizons at the same time, so both an outer horizon and an inner horizon that moves inwards with the collapsing matter. We have a bounce that avoids the formation of the central crushing singularity, a shock that forms, and that will eventually move out and reach the outer horizon after a lifetime of the order of the black hole mass squared. So one of the key points there is that this gives a limited amount of time for Hawking radiation to happen, and we would expect, just using the standard semi-classical calculations, the order of m quanta, each carrying total energy of about 1 over m. So you'd have a total mass that evaporates that would be of the order of the Planck mass in this case. So this would remain a perturbative effect at all times if this is correct. So this is the status of what we've been doing. And now a little bit about next steps. So I think there are some further steps that we can do within these effective models. So the first one is the question of covariance, which Christina already touched upon, and so have many other speakers at this conference. So I'm very optimistic about this. I think we'll be able to we have made a lot of progress on covariance, and I think we'll make more progress very rapidly as well. I think it's also important to develop more realistic collapse models. So far, we have collapse models that either are based on dust or a massless scalar field. So it'd be nice to have something richer there. And of course, ultimately, it's going to be very important to include rotation because the black holes that we have in our universe rotate. So this is a technically difficult but very important point to handle. Finally, all of the effective models that we have so far really handle the holonomies in the angular direction because these are the ones that are easy to handle, whereas those in the radial direction are much more difficult. And so I think it's an important challenge to address that as well. But ultimately, these effective models, I think, can be very valuable in answering some questions, but there are many questions that it can't answer. And for that, we really have to move on to truly quantum calculations, and this, I think, has to be a very important goal moving forward. So I was talking with Bea after her very nice talk yesterday, And she pointed out that to answer the question about purification, maybe we could do QFT on an effective background. And I think that would be a very interesting calculation. And we could see, is it possible to purify Hawking radiation using these effective models, but with a truly quantum or a QFT description on such a background. We could also use the new tools that Jonas and Thomas have developed to look at back reaction. And going back to some of the results that we have about the shock, I'd be very interested in seeing how the shock is manifested in the quantum theory and how to extract information from the shock in that case. So these are all open questions that I think are worth thinking about. Thank you.
Professor. So would you like to write?
I don't know if my slide will show up, but if it doesn't show up, I can say. So basically, I just want to say two things. One is that my general picture of evaporation is very compatible with what Carlo was saying. And I really do think that dynamical horizons are very important. What forms and evaporates is a dynamical horizon. And we have a, no, you don't see it. Okay, we have a very good chance of understanding the whole process, not only in the semi-classical region, which I think we basically can understand it very, very well, but also inside to the future of the transition surface up to the anti-trapping horizon. I think we can understand it, except for in both my talk and my summer school lecture, what I call the red blob at the end, and that I think is extremely hard. And there it is non-perturbative, it's going to be 1 upon h bar, and what is going to happen, and it's going to teach us a lot. But I think the rest of it we can still understand. But I think in terms of the thing that what we're asked to speak about is really about the future directions. And to me, as Ed already mentioned, realistic black holes are all rotating, and no approach, I think, not only loop quantum gravity but anywhere else, has looked at the rotating black holes. Now, in a curved black hole, because of perturbations, the Cauchy horizon becomes singular, and therefore, in fact, the singularity, a generic singularity, is going to be null. And I think various things that people have done in loop quantum gravity about singularity resolution, about the nature of the quantum geometry, trapping, anti-trapping regions, transition surface, etc. That I think really needs to be done for null singularities, not just space-like singularities. And to me, that is going to be like a pot of gold. It's not trivial, but I think one can start with simplified models, and there could be a lot of progress in that general direction. Thank you.
Thank you. I think next Arhana. Yeah. Can you hear me, Arhana? Yeah. So I'm
yes,
going to
I can.
move, your transparency. Okay.
I am sharing my screen.
Okay, yeah, you can go.
Do you see my screen?
Yeah, we can see.
Okay. Hello, everybody. It's nice to be with you. Thank you for giving me the opportunity to be there remotely. I hope the conference is going pretty very well. So my 2 minutes is one single slide. So quantum gravity is a difficult problem. We have made a lot of progress with the approach that we call loop quantum gravity. Loop quantum gravity is an approach where gravity and quantum field theory are expected to be emergent from an underlying discrete structure that is imposed to us due to background independence. So discreteness is this key prediction of our approach, and gravity, at long distances and smooth fields of quantum field theory should emerge from that only in the continuum limit. So this implies, in my opinion, and there are various ways of arguing for this, that there are degrees of freedoms that cannot be accounted for in an effective quantum field theory formulation or in perturbative quantum gravity. So this discreteness is crucial in understanding the origin of black hole entropy, and it is the heart of the calculation of the understanding that we have so far of of black hole entropy. I think there are many things to understand better on this corner, but experience from this tell us that in low energy accounts, when we talk about vacuum, let's say the Minkowski vacuum, that object is expected to be highly degenerate because of defects at the Planck scale. And in particular, the ADM mass, for example, is something we should expect to be highly degenerate because of this microscopic structure, these degrees of freedoms that are not accounted for in an effective field theory. Because of that, if these degrees of freedoms are truly there, and I believe that discreteness implies so, black hole formation and evaporation, which is a strongly time asymmetric process, as Carlo emphasized, perhaps it's the most irreversible of all possible processes, and because of the singularity, what we call the singularity inside, forces low energy degrees of freedom to interact with the Planckian degrees of freedom. So I believe that discreteness is key in understanding, in particular, the resolution of the black hole information problem. And that very same discreteness also leads to interesting phenomenology, like black holes as dark matter, which is a point on which we agree with Carlo, and we have written a paper we are very happy about. And there are many other aspects for future investigation. I think the hypothesis of discreteness and the idea that discreteness can have effects at low energy is something that is potentially, that has a lot of future. It's like at the beginning of the 20th century or the end of the 19th century, the atomistic hypothesis was not completely accepted by all physicists, and it led to a lot of progress, by Boltzmann, Einstein, and more recently, in the theory, examples like Landau and Ginzburg theory of superconductivity, from the hypothesis of discreteness, we can obtain phenomenology that can perhaps be very, very helpful also in guiding us in completing this dream, which is to have a consistent theory of quantum gravity. Okay, that's the framework that I would like, in which I am for answering the questions.
Thank you very much. Not bad. We just 1 minute, 2 minutes more than I think. We started late, 7 minutes. So okay.
Should I stop sharing?
Yeah. So I'm going to start the first question. Actually, I'm going to read this. Actually, audience can also see. The first question, I just changed a little bit of question. I didn't use the first person. It was argued that any QG theory must be holographic. Does any QG theory then resolve information loss or do no fork LQG representation render the arguments inapplicable? Yeah, I think perhaps you guys perhaps just if you want to answer, you raise the hand. Yeah. So then if you want to try to answer, you raise hand again. Okay. Yeah. Go ahead, please. Yeah.
Yeah. So I want to say that what Saurat has developed over the last several years is not, it's a paradigm. It's not a hard set of results. There are results, but there are also hopes, beliefs, and vision included here. If I just look at that paradigm is incomplete because certain operators that we would like to be well defined are not well defined, and we want to sort of to complete the paradigm, one would really have to do more mathematical work. It combines three aspects. The first is really the fact that Scri minus or Scri plus is a good Cauchy surface or a good initial value surface for zero response fields. Second aspect is really the Ray-Schlieder theorem, which says that in quantum field theory, if you give me any open region, and if you know, and the observable, if I know just look at the observables which are confined to this open region, and if I know the physics in that region, then quantum field theory is very rigid, and therefore I really has those things have information about the state everywhere. So in other words, any other observable I can reconstruct by looking at limiting process of looking at the observables associated with the open region. And the final thing is the Coulombic aspect of gravitational field, namely that you have got a ADM charge. And so he's putting these things together to come to this quote-unquote holographic. It's not completely holographic because it's really, you need semi-infinite region of scrap. Okay. So this general philosophy I don't think is incompatible at all with the kind of non-Fock representations of LQG or any other non-Fock representations. This picture is incomplete because it does not really include the massive particles. We are only looking at zero or smart particles at the moment. And so if you want to incorporate black holes, the question is how are we going to represent them, because you could have collapse coming in from infinity, from null infinity, forming a black hole and then evaporating. And if you say that it's completely evaporated away again, then that could be incorporated in that particular framework. But there's no inherent incompatibility or tension with ideas we are following in LQG, in my view.
Thank you. And if you want to, okay, I think our hand raised the hand. Okay, go ahead, please.
Yes. Yeah. I also want. I mean, I totally agree with Abai, but I wanted to add some other things because I mean that has to do with my perspective. So I find very interesting what Surat is doing. Okay, so if we. I don't completely agree that this, maybe it has to do with the completeness that Abai was evoking, that this completely resolves the paradox in the sense that just showing that there is no violation of unitarity is not all we want when we talk about resolving the paradox. We want to have an account of how is it that things that fall into the black hole end up coming out to purify the Hawking radiation, etc., etc. And I think in this sense, things are not completely clear. I mean, we could say, from the covariant quantum gravity perspective, that everything is obviously unitary because in the physical Hilbert space, all the Dirac observables are constants of motion, and therefore, whatever happens in the black hole has to preserve unitarity because there is no time evolution. Everything is registered from the very beginning in the choice of your physical state. This is the, some people call it the problem of time. It's a feature of quantum gravity when formulated the way we do. So that's one statement. The other thing is that in the process of Hawking radiation and black hole formation, there are degrees of freedom that are confronted, as I said before, that fall into the singularity, that are forced to meet the UV physics. And Surat is assuming, a low energy description of gravity. He's using, if I understand correctly, perturbative quantum gravity, and we don't really know what those degrees of freedom near the singularity are. So he's making assumptions about that, and that's very, very. I mean, we all make assumptions, but these assumptions can be violated by reality, by physics. In particular, if, as I claim, or I mean, if my hypothesis that I expect to be something verifiable from the full theory of loop quantum gravity, of course, that the vacuum is degenerate or the ADM mass is degenerate, then his claim doesn't work any longer. I mean, it is possible to actually create states which you cannot read from infinity because these defects are not Coulombian, if you want. I mean, they are actually, so these defects actually don't affect the ADM mass. So basically, the assumptions these assumptions are questionable in the context of loop quantum gravity, and this is how I see that, discreteness can be compatible, and the viewpoint I have about information in the information resolution can be compatible with Surat's statements as long as the low energy use of freedoms is concerned, yet these microscopic degrees of freedom can still be the relevant ones in describing the resolution of the paradox.
Thank you very much, Rahel. So we start from next. We try to finish all the 11 questions. So the second one, I'm going to read it then. Yeah, Carlos want to, yeah, okay.
What's the second one? Second question.
Oh, second one, okay. Oh, let me first read it, then you ask. Okay. Second one, what are the different perspectives and current outlook for understanding the original black hole entropy? Yeah, Carlos, please, go ahead.
Thanks. I raised my hand because maybe 20, 30 years ago, I wrote a paper together with Don Marolf and Ted Jacobson, a three-person paper in the form of a dialogue, actual trialogue, that's how we called it, on this question. And of course, I forgot about that, but I took a look about it recently, and it turned out that at the time there were two opposite perspectives, two opposite answers to this question. And all these decades have passed, and I think we are still disagreeing about exactly the same point. So the two answers are following. So I would formulate the question the following way. Black holes do behave thermodynamically. It's pretty obvious in a number of manners, because of temperature, because of exchange of heat and work. So it makes perfectly sense to associate an entropy to them, which is a thermodynamical entropy, which is quantitatively given by Bekenstein-Hawking entropy, is proportional to the area. And now there are two ways of interpreting that. These are the two solutions that were different at the time and still different today, and I think it's related to what Alejandro was saying. One, which is the one I defended at the time and is still defended by many people, and I think it's largely dominant in a relativistic community, is that this entropy, this thermodynamic entropy, is determining what happens on the horizon. So on the horizon, there's something happening which affect what you measure from outside, because of course the horizon can be dynamical, can move, can shake, have quantum, whatever. And that's what determines the thermodynamical entropy. The other perspective, which is connected to the question about holography, is that actually that thermodynamic entropy counts the possible number of states, the total number of states of the black hole, including what you would see if you fall in and you could measure things in. I'm still convinced, in fact, I'm more and more convinced, and I'm not the only one, that this second perspective is based on some misunderstanding of just forbidding oneself to look at anything else but boundary asymptotic observers, assuming that there are event horizon, that the horizon is forever, making what Madlacina calls the holographic dogma, the main dogma of black holes, and is physically not correct. But there's a big part of the science community that think the opposite and think that the total number of black holes it's given by the area, so that the answer to the question is that it counts the total number of black holes versus it counts only the number of black holes that can be measured from the outside, as long as the horizon can be approximated as an event horizon, so as long as we don't wait for the end of the evaporation and see what happened next. And the relevance is that, of course, if there are more black holes inside the horizon, the von Neumann entropy can be higher than the thermodynamical entropy, because one can be entangled with the degrees of freedom inside the horizon, even if the thermodynamical entropy is just decreasing because the horizon is becoming small. So the so-called page curve, the so-called black hole information paradox, they all depend on the assumptions that the inside of black hole is completely determined by what is on the boundary, which is an assumption which, again, I repeat, I'm completely not convinced about. I would stop here.
Okay, yeah, quickly, please.
Yeah, it's really, I mean, my view is exactly the same as Carlos about what the entropy counts. It is really the number of degrees of freedom that can communicate with outside. I just wanted to say that there is a simple contradiction between three things. One is that the black hole entropy is given by the area. The second is that it counts the number of states inside the black hole. And the third is the generalized second law. You can check quickly that there is a contradiction. One of them has to go, and many of us in this room think that, that the number of states inside the black hole, the number of states is the area counts that would have to go. So I think that's is a contradiction, and one of them has to go.
Okay, thank you. I will cut here because we try to answer all the 11 questions. If you have others answer later, I will. Okay. So the third question is, what is the hope for describing the physics of the tail ion of black hole evaporation when semi-classical matter fail using spin forms? What's the E to remain? Okay, Ed, please. Yeah.
I mean, I think there's been a lot of work showing the progress with numerics, and I think that there is a real hope of being able to do that. And maybe Carla will want to say a little more about that. But I'd like to also raise another possibility. So if you have some other physics that's happening, for example, the presence of a shock, then your lifetime can be much shorter, and you may be able to describe this in a more effective fashion. So we won't necessarily have to describe the very last seconds of evaporation when you have a Planck mass left. The physics may be different. But if that does happen, I think we've made a lot of progress with numerics, and spin forms will be able to do that. I don't know if Carla wants to add to that.
I would say.
Okay, yeah.
I mean, no, I find it very implausible that the mass of the black hole, that the evaporation time is m squared or m or something like that. If that were the case, that means that the Hawking radiation is totally irrelevant. Now, that's a point of view you can take, but I just don't think that's, it's a personal prejudice. Because by m squared, almost no Hawking quanta are emitted, and then already the black hole is gone. So there's not, so that viewpoint, it's not impressed upon young audience, that viewpoint says that Hawking radiation is totally irrelevant for physics, and I don't share that point of view.
Thank you. Yeah. If you do not have more, let's turn to.
Can I say something?
Yeah, go ahead, please. Yeah.
Yeah, I just wanted to add that, something I had in my first slide. So one thing that one can see is that near the singularity, generically, we have large quantum fluctuations. Because, that's not necessarily the case in the effective model that people are studying, but this is because of symmetry simplification. So tiny deviations from symmetry get blue shifted towards the singularity. So it is, and this, because if you consider Hawking radiation, you have a superposition of different quanta, in the thermal, you have thermal radiation going to infinity and partners falling into the singularity with all possible, quantum numbers in a thermal spectrum. You have a superposition of very, if we think naively, very different geometries, and so the quantum geometry near the singularity is very far from whatever you can describe in these spherically symmetric models. So if we want to actually understand what happens at the last moments of the operation, and before I say so I think this is possibly the reason why we're finding these numbers. Like, I agree with Abai that it would be very strange that the black hole will actually evaporate in timescales smaller than m to the third. Maybe the things what they're finding is because of the type of models we're using. And so we have to try to take into account these very large fluctuations near the singularity, and the only tool I see that can plausibly be applied is spin forms. So in that I agree with Ed. Probably, it's hard at the moment, but that's, the strong UV regime will have to be treated non-perturbatively and not with symmetry-reduced models. We have to include all the local degrees of freedom.
Okay, thank you. Yeah, let's go to the next question. So I'm going to read again. What's the status of understanding the Hilbert space for a quantum evaporating black hole what obstacles remains? Anyone, if you want to answer a question? Okay, Carlos?
If nobody
okay,
else has something to say. Um, I will comment about the question. What is the start of our understanding of the Hilbert space of a silver atom? Well, depend. It's very simple Hilbert space. What is the status of our understanding of an ammonia molecule? Okay, an ammonia molecule is treated in many of our elementary quantum mechanics courses as C2 is the Hilbert space of ammonia molecule for the purpose of the left-right blah blah story which we do in courses. But of course, we can do molecular dynamics. Then we have a much bigger Hilbert space in which we have the electron. But of course, we should remember that this whole atomic physics is much bigger Hilbert space. So I would be very careful in interpreting these questions correctly. So if the question is, what is the total Hilbert space of a big black hole? I don't know, what's the total Hilbert space representing you? Is do we care? But if the question is, what is a proper Hilbert space for describing the evaporation, then it's interesting because, we can physically try to understand what are the relevant Hilbert space, the relevant degrees of freedom, describe those ones and count them and got an entropy. It's for all the work that was done on the puncture on the observables. So I think we have good understanding of some aspect of a possible description of Hilbert space that describes some aspect like entropy. I mean, this is loop quantum gravity calculation of entropy. So of course we have an Hilbert space for that, but I have not seen anything convincing, fully convincing about using this Hilbert space for describing radiation itself, nor for describing the more degrees of freedom relevant in the interior of the black hole. I don't know if other people agree with this.
I think that if one is only interested in the evaporation process, of course, one should work in Heisenberg picture, and therefore the Hilbert space is really the Hilbert space of the incoming quanta. I'm talking about not stellar collapse now. Again, I'm talking about a closed system. So the quanta that came in, the Hilbert space of associated with Scri minus, the scalar field or whatever it collapses. That's it. And then you got all these observables, which are very, very interesting inside the black hole and such thing. And these observables, together with these states, give us different physics. So Hilbert space is not that interesting in this point of view, right? It's the interpretation of elements of this Hilbert space that is trivial for the incoming particles, but near the dynamical horizon, near infinity, it's very, very non-trivial, and that is what is worked out. So Hilbert space is not the key point at all, but the observables are the key point, I think.
Okay, thank you. Let's go to the QT or LQT effect around the singularity property significantly to the...
Maybe, can I add something?
Yeah. Oh, you want... I think...
you hear me?
We still have several questions. Would you mind
Okay,
we do
okay.
next? Because I want to cover all the 11 questions to be fair with the audience. Is that okay? Thank you.
It's okay, it's okay.
Okay.
Yeah, let's go on.
Yeah, okay. So for example, a factor is out of equilibrium dynamics and quasi-normal mode. Yeah, this is a question.
Yeah, I think quasi-normal modes in general are interesting, in particular now if we, for some models, can link to modified covariant models, it would be interesting to consider perturbation theory in that context. What one would naively expect also for these effective metrics is some modification in the effective potential. However, whether this has some observable effect, I think is still under debate. And in this sense, at least I cannot answer this question in a way that there is a yes or no, but this would be the direction in which I would think about this.
But the concrete calculations by the Spanish group and the Madrid and the Canadian group actually have calculated these in certain loop quantum gravity black hole models, and the effects are totally negligible, the quantum corrections. The reason is just because outside the potential, outside the horizon, the quantum corrections are negligible. So therefore the cause is not, so therefore the potential is not changed at all. And so there is change, there's a difference, there's a quantum correction, but it's of the order of 10 to the minus 25, 27, and that's not very observable.
Okay, thank you. So let's go to next, so we can save some time. Next question is, loop quantum black holes operated so far from effect theory have different properties depending on the choice of gauges. Is the dependence due to the nature of LQG or to something else? Yeah, Christian.
Yeah, I think it's a question probably one can also address in classical gravity already, whether something you see depends on your gauge or on your coordinate choice. I think it's even not the case, at least if the two of us talk, we wouldn't say our results do not depend on the gauge. Finally, I think we have agreement for the models that we considered in similar gauges. And I would say it just shows, and this was on my slide, that gauge fixing at the effective, or even if you can do it at the quantum level, is more subtle than if you do it classically. And we just have to take care in interpreting our results, and maybe always, if possible, go to a gauge unfixed version, because in this case it was quite useful to get this broader perspective and then consider different gauges.
Yeah, no, I agree with that fully. I think as a first step, it's often easier to work in a gauge fixed setting, because then you can make progress, but then ultimately you have to make sure that what you have is covariant. And I mean, the work that Christine and her collaborators have done has really shown that we have the spatial diffeomorphism constraint is still there, so that's very nice. And we still have to do some work to make sure that the time-like diffeos are there. And I'm very encouraged by a lot of the work that we've seen at this conference that's been looking precisely at these questions of covariance. So I hope that we'll have a clear answer on that soon.
Okay, thank you. Any other comment? Okay, so I will go next. Let me see. Okay, third approximation in black hole evaporation. First, no backscattering. Second, geometric optics. Third, semi-cluster back reaction. Which one should we draw first to make progress? Carol.
So first is a great question, and I don't know who sent it, but whoever sent it should be
Eugenia.
Okay, so whoever said it should be sitting here and comment and give the answer. All three, of course, but I would find backscattering particularly interesting to add to the picture we got from, the beautiful picture we got from Bea yesterday, because of trying to track where the information goes. If you forget backscattering, the information with whom the whole congregation is entangled comes out from that, in that particular, in a bias picture from this blob, from this thing that we call the B region, from where the non-perturbative quantum transition of the horizon happens, should all come out there. And if I had to bet, I would say that this is wrong. And if you include the backscattering, it's a bet. So just if you include the backscattering, information goes far more inside, so it comes out much later. But I don't have a calculation supporting that. So I would love to see it.
Thank you. I think Alejandro just raised the hand. Okay, go ahead, please.
For the reasons in particular, agreeing with Carlo, one of these assumptions should go if we want to understand the fate of information. And unfortunately, is the hardest one, which is semi-classical back reaction. I mean, near the singularity, there are big fluctuations, but if you do semi-classical back reaction, then the Hawking radiation is just spherically symmetric and nothing seems. So it is actually in the fluctuations where the particle the information of the partners that are correlated with the outside radiation goes, and so without throwing three things will remain incomplete, in my opinion.
Eddie, can you quick comment? Yeah.
Yeah. So of course I'd like to get rid of all three. I mean, everyone would. But as a first step, and maybe not necessarily the most, the easiest thing to do, I think, is none of those three, which would be to keep those three approximations, but to do the same calculation on a different background that's motivated by these effective models. And that could give some guidance as well. But of course, that's a first step towards getting rid of these.
Thank you. Yeah. So let's go to the next question is, can non-perturbative effects of various asymptotical quantization be studied in the framework of LQG? Is there any chance to observe signatures from merging black holes? Okay.
So,
yeah.
yeah, I mean, non-perturbative. Yeah, the non-perturbative effects of asymptotic quantization, you can actually, you'd be able to easily see them in the LQG picture. The basic reason is because the, I mean, in the asymptotic quantization, the fundamental variable is a connection, so you can use holonomies, and so in terms of, make the algebra in terms of holonomies, and therefore one should be able to see it in the LQG picture. But there are obstructions, and I can discuss that privately later on. What the things to be solved. I don't mean obstruction in the sense no-go theorems, but there are the current LQG framework has to be extended a little bit to do that. And the last question I don't really understand. I mean, you were talking about black hole mergers. Are we?
Gravitational waves, I suppose.
Yeah, gravitational waves. So I mean, is one talking about quantum gravity? One is classical gravity. Classical gravity, of course, we had a lot of signals from black hole mergers. And if the question is about quantum gravity effects from astrophysical black holes, of course, there are different communities pushing hard to say that there may be quantum effects that may be detectable by LIGO. I personally don't think so, just because the quantum effects outside the horizon of these black holes is extremely, extremely small, in my view, in all the LQG effects and so on. And so I think it's unlikely, but you know, that is my personal perspective.
Thank you. Okay. Any other comment? Okay, good. We'll save some time to next. So next question is, what is the operational meaning of a Penrose diagram in a regime when quantum effect of gravity are strong? So Alexander, this is a right hand. Please go ahead, Alexander. Yeah, go ahead.
I think this is a great question, because if one takes into account the large fluctuations at the singularity, then can I share my screen? I wanted to show a picture. Then there are strong reasons.
Yeah,
do you see my screen?
Yeah. Okay, good. Go ahead.
Then in the quantum gravity region that we are all familiar with, is expected to be a region where very, very strong quantum fluctuations occur, and maybe we cannot actually represent this in a single space-time background, and that's something that it's often emphasized. But what is less often emphasized is something that it's been known for a very long time. Already Page in the 80s, I think, he did this calculation, which is a very simple calculation. And so if you assume momentum conservation, then the Hawking radiation you receive at infinity is a superposition of quanta with different quantum numbers. And in particular, when you have one quantum in this superposition, there are particles with a given momentum. And so by conservation of momentum, you would expect that the black hole would get a kick each time it emits one of these particles. So the black hole is actually in a superposition, entangled with this Hawking radiation, of black hole getting little kicks in one direction or in another. Of course, if the quantum is spherically symmetric, there is no kick. So using momentum conservation, and because the Hawking radiation is so slow, it takes a very long time for this for the mass of the black hole to shrink. He realized that by macroscopic time, the black hole would be in a linear, in a superposition of states at different positions, and that the dispersion in position grows to up to the order of m squared by the end of evaporation. So, in fact, we might hope to, when we draw these pictures with Penrose diagrams, like the one you find here on the left, in fact, this is not quite appropriate, and it's not really taking into account this feature. So a more appropriate picture is something like the one I try to represent here on the right. So it is challenging actually to represent with Penrose diagrams what is actually happening in Hawking radiation. If we consider the unitary evolution, then at the end of the evaporation, we have a superposition of black holes, ending the evaporation at different places with a very, very big dispersion. And this is only one aspect, an aspect that was investigated by Page, but we should expect that to the future of the Wood-V singularity, there would be large fluctuations. And so the state of the quantum geometry will be a superposition of things that each of them looks quite close to Minkowski, but they are not quite the same Minkowski spacetime. And so, and of course, this goes together with I think this is something that we should take into account when we discuss unitarity, the unitarity of the black hole evaporation.
Thank you. Yeah. Let's go to next. Okay. So now this, do we need superpositions of space-times and of course structures to understand black hole evaporation? So anyway, yeah, okay.
Okay, so there's a long phase of semi-classical phase in which the black hole is still macroscopic, and there I don't think we need any superposition of space-times. It's true that during that phase, the black hole is actually, the dynamical horizon of the black hole, there's the influx of radiation, carries momentum, energy, etc., and that just changes the multiple moments of this black hole, of this dynamical horizon. And so I think it's all this influx, the momentum considerations are all encoded in the multiple moments of the dynamical horizon by itself.
Not the linear momentum. The linear momentum is a kick. The linear momentum is a kick, right? I mean, it's one of the moments, but
yeah, but I mean, even in the
case of superposition,
even in the case of classical black holes, when they merge, there is a radiation that is falling out into the dynamical horizon. It's not that it goes out only at infinity, and of course there's a kick, but that kick is all completely described by just the multiple moments of what is happening on the horizon. That is.
It's a moving horizon. But it's a horizon moving away.
You should not think of black hole as a point particle, which is getting kicked.
I don't think of a black hole as a point particle. It is moving. I mean, these kicks exist classically.
Yes, of course.
In quantum mechanically, yes.
That in the sense that it moves in the sense.
But here we have a quantum superposition nearby. So you're going to have one moving in one direction and one superimposed with another horizon moving in a different direction.
Yeah, that's the reason why the final black hole can actually be moving with respect to the galaxies, with 1,000 or several hundred kilometers per second because of the.
I meant the quantum. Yeah. I meant the quantum portion of it.
So I will let you to later, last 15 minutes to ask questions. Thank you. Yeah. So let's go to the last question because I really want to save a couple of minutes to the general audience to ask current question. So this is the last question in my list. Is there a meaningful notion of causality in the quantum regime of a black hole space-time? Sorry, I just missed one. Yeah.
Oh, here, Ed and I should have a good fight here. You go first.
Yeah, Ed, go ahead.
So, well, why don't you go first?
Okay.
So one thing I've been discussing with Ed is that in the shock waves scenario that he and Vicar and the collaborator are considering, shock wave moves sort of space-like, right, in some sense. So there is a sense in which there is a region of space-time which is still very little quantum, maybe. This is all very vague, in which you can have by causality you should expect that nothing happens, but something happens. So there's a sort of violation of causality. That's one thing we've been debating about the shock wave.
Yeah, so I mean, the idea is you have this discontinuity in the gravitational field, And according to the interior, you're moving in a causal way, and according to the exterior, you're moving in an acausal way. So the question is how to interpret that.
Right.
Yeah.
So question mark is
Yes.
here, I think.
Okay, thank you. So this is the general question I have, right? Well, only two questions, okay? One, yeah.
So I wanted to clarify something about the first question that was asked, since there were some remarks about some of the work that I was doing. I want to first say that it wasn't me who asked the question, so I don't know who it was who asked the question. I think one of the things that Alejandro said was that there wasn't a clear physical mechanism for what happened. But I think that I want to emphasize in these pictures of where you take holography seriously. There is a physical mechanism for how the information emerges, and it's pretty simple to understand. It's the fact that, just remember, classically, we've always agreed that you always have information about the mass of the black hole that never goes in. And that's true classically. And the statement is that quantum mechanically, if you keep track not just of the expectation value of H, but all correlations of H, then that keeps track of everything that went in. So the mechanism is that, the no-hair theorem fails, and you can see this very explicitly in the low energy theory. Now it's possible, of course, that at some point, the assumptions that are made break down and there's some phase transition and something dramatic starts happening. But if you just take these low energy effects, which you can calculate very explicitly, and you make some reasonable assumptions, the fact that energy is positive, vacuum is unique, which as you said might or might not be true, then you would extrapolate this all the way to black holes. And it's true, as Abhay said, that we don't have a complete incorporation of massive particles because massive particles are hard to describe at Scri+. But if we take a large enough black hole, then we would expect that most of the information does come out at Scri+. Now again, we could debate that. But I just wanted to say that there is a fairly clear physical mechanism, and which you can see and verify in effective low energy field theory. And it's a pretty reasonable extrapolation then, I think, to the ultraviolet physics that would suggest that this, the mechanism would be the information never goes in. And
Subrat?
Yeah.
Thank you. Yeah.
Can I ask you a question, Subrat? Is there one of the assumptions, the one that Carlo was referring to at the beginning? Do you assume that the number of states of the black hole are given by the area somewhere in this picture?
No, because in fact black holes are not very crucial. These arguments are made.
No, but there are places where you say there are small corrections that are, exponentially small in the area of the black hole and things like that. Good. Aren't you assuming that the Hilbert space is finite dimensional?
No, I don't think we're assuming the Hilbert space is finite dimensional, but I think we are assuming that the Hilbert space is given by the set of all states that you can form from collapse. So, if you think of the set of all states you can form from collapse, then, we're assuming that that is the full Hilbert space. The e to the minus s is really an estimate. It's an estimate of what size you expect the corrections to be. The argument doesn't rely on the fact that the corrections are e to the minus s.
Okay, thank you. I think I will cut here. Your second question?
Sorry, can I answer this one?
Yeah, good.
This is true once you form a Hilbert space of a certain area of the horizon. But then the question, there's no problem with that. The question is what happens when the area shrinks. That's the problem, okay? When the area shrinks, you go in after the area shrinks, okay? Inside, your local quantum field theory operators can detect more states than those determined by the area. And if the answer of that is no, then you're violating quantum field theory locality, period.
I think the answer to that would be no, although that would take us into a second question, might be a longer debate.
Can you discuss later?
We can discuss later.
Okay.
Yeah.
Thank you. Let's go to the second question. Yeah, quickly, please.
Of course. I have two very short comments and a question. One of the short comments is something that I wish somebody had told me when I was a younger student, which is reinforcing what Alejandro said, be very skeptical of Penrose diagrams. They're an incredible tool. They carry the causal information, right? But don't overread beyond that causal information because often it misses a lot of the physics. And the reason I'm saying that in this context is just to comment on one of the things Abhay had said. Eugenio and I did think about the rotating black hole case. I think Abai was referencing the fact that nobody's built a full, non-perturbative evolution over all times, but we thought about spin fluctuations, and we have good evidence that the onset of quantum gravity is before you get to the Cauchy horizon. So if you look at the Weyl scalar, which envelopes both the Euler-Pontryagin scalar and the Kretschmann invariant, the onset of quantum gravity, that is, curvature becomes Planckian well before you get to these null horizons. It's a space-like surface, and so it's much more like Schwarzschild in that sense, in the sense that Planckian curvature is space-like. So that's my comment. For me, the Penrose diagram, I always saw these infinite extended curve, but that's not physical at all. You should cut it off before you get anywhere near any of that extension. And somehow we take the mathematical extension too seriously. My question's in a totally different direction. We talked about the long-term future of black holes. We're very interested in this non-perturbative completion, but I want to know a little bit more about the memory comment you made yesterday, Abai. You said that you had already found some signatures of memory in the black hole mergers that we've already seen, and you compared it with the way in which we infer black hole masses. So the question is in two parts. One is, would you say that it's definitive that we've seen memory?
Yes.
And then, are there hopes for us to extract something about quantum gravity from memory?
Thank you.
No, I mean, okay, we will discuss it in greater detail, but no, I mean, I think there's a memory, but from the signal, one can actually draw the probability distribution, like all observables, like the mass of the final black hole, spin of the final black hole, you have got probability distribution, you draw the probability distribution for the memory, and it's non-trivial, and for many of these LIGO events, and so that is what the status is. But I don't see, I mean, the non-trivial memory then gives rise to infrared effects and infrared sectors of quantum gravity, etc. But that is not directly seen anywhere. So those are theoretical implications in quantum gravity of this memory. I mean, so if you like, it reinforces the idea that yes, there should be quantum gravity should take into account infrared sectors.
Thank
you for reminding me about the perturbations, because I had forgotten completely about it. That's a good point.
Okay, thank you. I think perhaps we should go to the last so in terms of 15 minutes, the panelists ask a question each other. I think first each one asks one question, then we go around, okay? Yeah. So, okay, who wants to ask first?
So I can ask the first question.
Go ahead, please.
So why to all of you, why do you think that the effective models are, I mean, do you think that do you think that is, what do you think that the effective models are good enough to address the question of black hole evaporation when there are that don't seem to have fluctuations built into them? I mean, they are classical, right?
Anyone want to answer first?
So you're looking at the effective models in which there are no fluctuations built into them. That's a question, right? I mean, and why are they good enough for some?
I mean, all the pictures, most of the pictures are drawn based on models which are spherically symmetric, and one does not use the quantum theory. One uses the effective dynamics. And so, even though they avoid singularity, the question of fluctuations near the singularity is completely out of the model by construction. Isn't that an issue if we want to describe black hole information?
Yes.
What happens with the black hole information?
Yeah. So, for example, if I take this AOS model, then this, one is completely ignoring the dissipation there, these fluctuations there from the. I mean, one is not. Yeah. One is ignoring the Hawking radiation, these kind of fluctuations there. One is not ignoring all the quantum effects, of course, because there's a quantum effects which is all the singularity. And so one should not take the.
But it's not a quantum theory. It's an effective theory.
Yeah. So in the effective theory, there is a resolution.
Why is it good at the Planck scale? That's my question. Maybe refining the question.
What one sees, this effective theory is telling us at Planck scale is that if you like, in the effective theory, the curvature singularity is resolved because there's a negative energy density, if you like, right? Because otherwise you'll have the singularities happening. If I just write down Einstein's equation in a different way, then there'll be singularities that is happening. Yeah, so one should not take these things too literally. They're to be taken only as guidelines. And the idea is that if in fact, and so this tells you, now I bring in radiation, I bring in the Hawking radiation, and then the statement is that indeed the mass of the black hole is going to be changing slowly, right? I mean, because of the Hawking radiation. But there is also this negative energy which is coming in because of loop quantum gravity effects. And why does one trust that? Because one trusts the loop quantum gravity effects in, if you like, in the cosmological models, where one has looked at perturbations, fluctuations, and their effects, and so on and so forth. There are assumptions. There's no question about it. So we do have. We are using the lessons learned from the effective model, but not literally, because you have to really take into account what Carlo would say dissipative effects of the Hawking radiation. Now, if the mass is changing very adiabatically, then one can say, okay, in that little region, I can actually use an effective description again. And in other words, if it takes 10 to the 67 years, then maybe for 10 to the 10 years, I can actually assume that the mass is almost constant, and then this effective description could be a good description. These are guidelines. They all will have to be verified, but the question is, it's providing a little bit of intuition to take one step ahead. So it's not meant to be a, anyway definitive answer.
I mean, I would add to that. I think we can learn from looking at cosmology in this case, because in LQC, of course, we first built the quantum theory and solved the dynamics, the quantum dynamics, and then found that the effective equations followed it very closely. And that's what told us, okay, the effective equations do capture some quantum effects so long as we're dealing with sharply peaked states. And we had some arguments now that we understand that so long as we're looking at cosmological spacetimes where the spatial volume and the spatial length scales are large compared to the Planck length, it is possible to have states that have small quantum fluctuations and where we can trust the effective equations. We don't have any of that understanding for black holes yet. So this is something that has to be developed. Sorry, just let me finish on that.
Yeah.
But I think it's a reasonable hope, again, a hope, not a proof, but it's a reasonable hope that these effective equations can hold and can capture quantum gravity effects so long as we're dealing with black holes that have a very large mass. At some point, of course, if we're dealing with black holes that have a small mass, then this will break down completely. But,
so I'm sorry, I have to cut here because we have a permanent talk. I think Alejandro is the only one remotely. I only allow him to ask a question. You four guys, no more question. Okay.
Thank you.